Good morning, calculus class. The notes that we're taking today are on something called the quotient rule. So you've heard of the product rule. If I'm multiplying a product, there's a way of doing that. And today, if you have a quotient, it's going to be a little bit different. The product rule, which I don't think is intuitive at all, if I wanted to take the derivative of a composition of functions, it turns out that it's not just f prime times g prime. The derivative ends up being f of x times g prime of x plus f prime of x times g of x. The question for today is, what happens if I want you to take the derivative of a composition, or excuse me, not composition, a quotient of functions? What's this going to be? And I'll tell you in a little bit. So, first example, can we take the derivative of this? And first of all, I'll tell you what's not the derivative. It's not the case that the derivative is taking the derivative of the top, which is 3, and the derivative of the bottom, which is 3x squared. So this is not the derivative. So I don't know. Big no. It's not the case that you can take the derivative of the top and the derivative of the bottom, and that's the derivative of the quotient. So if we had to do this, we'd first have to rewrite it. So f of x, I'd want to rewrite it so I can use the power rule, and we can cheese it a little bit. This is just 3x over x cubed plus 5 over x cubed, which is the same thing as, so let's see here. This x is going to cancel out with one of those x's, so there's 2 down here. And this x to the second on the bottom, I can bring upstairs and make it 3x to the negative 2. And this 5 over x cubed, I can rewrite as 5x to the negative 3. Cross the line, change the sign. And now taking the derivative is just a power rule. So it's going to be negative 6x to the negative 3 minus 15x to the negative 4. Not that difficult of a problem. And it's only doable because we can rewrite this quotient as 3x to the negative 2 and 5x to the negative 3. That's kind of like adding two power functions. Here we have an issue. You might want to like rewrite this as like, I don't know, x squared over x squared plus 1 over 2x, but that's it's not the case that those are equivalent. If I wanted to rewrite it, I could rewrite it as x squared over x squared plus 2x plus 1 over x squared plus 2x. So they have the same denominator. But again, that doesn't really help me here. I can rewrite this as 1 times x squared plus 2x to the negative 1 and x squared times x squared plus 2x to the negative 1. Again, we have a product here, and we also have a function inside of a function to the negative 1. There's a lot of issues with this. If there was just one thing in here, like x to the third, then we can write this as x to the negative third, and then that would just be, it's a multiplication symbol, and that would be like x to the negative 1, and then we'd be okay. Taking the derivative, that's no problem, but because we have two terms in here, we're kind of screwed. So that method that I did on the previous example doesn't work here, and we need a rule for taking a derivative of a quotient. Again, it's not the case that the derivative is 2x over 2x plus 2. I just took the derivative of the top and bottom. Again, it's a hard no. Think of Michael Scott when Toby returns from his trip. No, God, please, no. Okay. So then, how do you do this? We'll see about that in a second. So if I do have a quotient, I want to take the derivative. It's not intuitive at all, but it turns out that the derivative is take the bottom function multiply it by the derivative of the top function, subtract that from the top function times the derivative of the bottom, all over the bottom function squared. Again, very unintuitive. I'm not going to prove it for you, but similar to the product rule proof, it's another add zero proof. If you're interested, I'd love to show you. But this is what you're going to end up, memorizing. There is a way to memorize it that the seven dwarves have come up with. Ho de hi minus hi de ho over ho ho, or ho squared. So think of hi as the top function and ho as the bottom function. Then the bottom function is ho. D high is the derivative of the top function. So ho d high minus the high function, which is f of x, times the derivative of the bottom function, which is d ho. And the bottom function squared is ho ho, or ho squared. I will actually call this low d high minus high d low over low low. I won't use ho, I'll use low instead, but do whatever you want. So, a quick shout out to the seven dwarfs. Thanks for the quotient rule.
Hi ho, hi ho, hi ho, hi ho, hi ho, hi ho, it's home from work we go. Hi ho, hi ho, hi ho, hi ho, hi ho, it's home from work we go. Hi ho, hi ho.
You get the point. Okay. So now we can actually go back to this original problem. If I have a quotient here and I want to take the derivative of it, I don't want to write f of x in two different spots. So I will write f over here, but it's not going to be the same f over here. In general, if I have a quotient of functions, then the derivative is going to be the low function times the derivative of the top function, so low d high minus high, the high function, times the derivative of the bottom, which is d low, over low low, or low squared. So low d high minus high d low over low low. You're going to hear me saying this enough times where whatever I just said will eventually make sense. But the bottom function times the derivative of the top minus the top function times the derivative of the bottom over the bottom function squared. Why is this the case? Again, we could prove it with the limit definition, but for now, let's do it. All right, so I want the derivative of this function, and it's the bottom function times the derivative of the top function. The derivative of the top function is just 2x minus the top function, which is x squared plus 1 over the derivative of the bottom function. The derivative of the bottom function is 2x plus 2 all over the bottom function squared. This will take a while to make sense, but we're going to get good at it after a couple of reps. Again, so this is if I were to call this bottom one the lower function, and this bottom one the top function, we have the bottom function low d high, that's derivative of the top, minus high d low, all over low low, or low squared. So again, g of x is the x squared plus 2x. F of x I'm calling x squared plus 1. I know this whole thing's called f of x, but I don't know. Think of it as a different f. Bottom function times the derivative of the top minus the top function times the derivative of the bottom, all of the bottom function squared. We'll get some reps in and make more sense of this later. The derivative is done. Now we just got to simplify. So I'm going to distribute here. So it's going to give me 2x cubed plus 4x squared minus, before I minus, let me just FOIL these johns. X squared times 2x is 2x cubed. X squared times 2 is 2x squared. 1 times 2x is 2x, and 1 times 2 is 2. All over this bottom john squared. So, by the way, this is going to become, no, there actually are no like terms here. So I'm just going to distribute this negative in, so those all signs change. So then I have 2x cubed plus 4x squared minus 2x cubed minus 2x squared minus 2x minus 2 all over x squared plus 2x squared. And these are going to cancel out. And then we have a 4x squared minus 2x squared. That's going to simplify nicely to 2x squared. We still have the minus 2x minus 2 all over x squared plus 2x squared. Again, don't multiply at the bottom. Just leave it alone. It's fine as is. Yeah. And so that's it. So that's the derivative of the function. All right. So try a couple on your own. Do pause it. Actually, see if you can get these on your own. I think it is worth trying to like look back and forth. Although I know if you're busy and you got to get this done as fast as possible, you might not want to do that. But it's good for you. All right. So if you pause it, you hit play. All right. So to take the derivative of the function, we have a composition. Excuse me. We have a quotient. So it's going to be low d high minus high d low over low low. So the bottom function is low. So low d high, the derivative of the top, minus high d low, the derivative of sine of x is cosine of x, all over low low, which is sine of x squared. There's not really much simplifying to do. I'm just going to write the first part as 2x sine x minus x squared cosine x over sine squared of x. And that's it. There's no other simplifying to be doing here, so if there is, we'll do it. So here I want to take the derivative of this function, and it's going to be the bottom function, so low d high, the derivative of the top is 12x squared minus 7. Low d high minus high d low. High is that, d low is that. All over low low, or low squared. All right, cool beans. Yeah, we're going to just FOIL these out, combine like terms, and circle it. So here's all the algebra. 5x squared times 12x squared is 60x to the fourth. 5x squared times negative 7 is going to be negative 35x squared. 2 times 12x squared is 24 x squared, and 2 times negative 7 is negative 14. I'm going to FOIL out multiply out the inside before I distribute that negative. So, oh wait, no, this is not a binomial, it's just 10. We don't have to do that. All right, so we have, think of it as distributing a negative 10x in here. So the negative 10x, let me just put the, I don't want to confuse you, but think of this as just a negative 10x. And if I multiply that in, I'm going to get minus 40x to the fourth, and then negative 10x times the negative 7x, going to give me a positive 70x squared all over this. So, like terms, 60x to the fourth minus 40x to the fourth, give me 20x to the fourth. Negative 35x squared plus 70x squared, that's going to be 35x squared. And then we have a plus 24x squared minus 14 all over 5x squared plus 2 squared. Uh-oh, I made a mistake. Oh, no, I didn't. We have more like terms. I just could have done it all together up here, but I was being a silly goose. All right, so let's do it now. I'm doing one extra step than you guys would have done. There's more like terms. So 35x squared plus 24x squared is 30, 40, 50, 9. x squareds minus 14 all over 5x squared plus 2 squared. Cool. And there's my derivative. Okay, so that's how to use the quotient rule. We'll get a bunch of practice in class. But now that we have the quotient rule, we can actually find the derivative of tangent, which we couldn't before. The reason why we couldn't before is because tangent, if you were to rewrite it, is just the same thing as sine of x over cosine of x, which is a quotient, which we don't have a rule for. So now we do. If I want to take the derivative, just remember low d high minus high d low over low low. So low d high, the derivative of sine is cosine, minus high d low, the derivative of cosine is negative sine, all over low low, or bottom squared. So that's going to be cosine times cosine is just cosine squared. The double negative is going to give you a plus. Sine times sine is sine squared over cosine squared. Now I know what you're all thinking. Cosine squared plus sine squared, that's like the Beyonce of trig identities. Everyone knows sine squared of x plus cosine squared of x is just 1. Right, so this is just, that's just equal to 1. A little prior knowledge there. And 1 over cosine squared, remember 1 over cosine is secant. So 1 over cosine squared is secant squared. So what's the derivative of tangent, you might want to know? So it turns out that the derivative of tangent x is secant squared x. If you don't want to memorize it, that's fine. You could always rederive it. So if I take the derivative of tangent, it's secant squared. All right, so what about these ones? And I don't know. Part of me just wants to make you guys do these in the beginning of class next time. Part of me says let's do them now. I'm gonna have you guys do these in the beginning of class. So do these on your own for part of like your homework. See if you can figure out what these are. But actually like do out the work because you can just easily Google what's the derivative of secant and get your answer. But it's gonna be similar to these ones up here. They're gonna work out sort of nicely. Some better than others. And in class we'll do them again and see if we got them. Anyways, that's it. Have a nice evening.